Let's get started. And I actually have, let's see, three different stories. And the first one is about a paper that just came out, and it has to do with metallic hydrogen and about what we think is at the center of planets like Jupiter. I'm using this new pointer system, so it's still getting used to it. So the paper itself is called titled Size and Strength of Self-Excited Dynamos in Jupiter-like Extrasolar Planets. And the main author is Mohammed Zaghu, who's at the University of Rochester. And but before we jump into the paper, first I want to talk about what exactly is metallic hydrogen. And first of all, we need to discuss what exactly is a metal. And so I'm sure most of you are probably familiar with metals in your life. But some of the characteristics of metals, obviously, anyone want to just shout out an answer? What was that? Conductivity. Okay, that's metals do conduct heat as well as electricity. Anything else? Malleable. Yep. You can form them. You can shape them. You can pound them into flat strips. Reflectivity. They're shiny. And so, yeah, actually, we've covered a lot of what I was going to talk about. They're shiny. They conduct heat. They conduct electricity. They're malleable, meaning you can pound them. They're also what's known as ductile, meaning you can shape them into wires. You can stretch them. And they tend to be high density. And it turns out, and along with a number of other different properties, but the key reason why metals have these properties have to do with the number of electrons that are in the outermost part of metallic atoms. And so if you look at the periodic table, this is something that should be familiar with anyone who's taken chemistry, but it turns out that much of the elements that we see out in the universe are actually metals. There are a number of nonmetals off in the corner here, and then there's also a strip of metalloids, or things that are kind of, they have properties of metals, but they also have properties of things that aren't metals. And then finally, also notice hydrogen over here is by its lonesome self, and it turns out that normally hydrogen is not a metal, but under certain conditions, it can have metallic properties. And so as I said, the metallic properties have to do with the fact that metals tend to have one or several electrons that are only loosely bound at the outermost part of the electrons that are in orbit around the atom. And it's those kind of loose electrons that give rise to the properties that we think of when we think of metals. So the fact that they tend to be shiny, they conduct heat and conduct electricity really well. And so if you can get, let's say, hydrogen into a state where you mimic those electron properties, you can actually turn hydrogen into something that's very metallic. And now here is what I call or what's known as a phase diagram for something that we're all familiar with, water. And what this shows is temperature at the bottom. And so we're going from 0 degrees to 100 degrees Celsius. So obviously 0 is when water freezes. 100 is when water turns into water vapor, when it boils. And then here along the side is the pressure in atmospheres. So the pressure at the Earth's surface is just 1. And then here we have down to 0.006. And then here we have a couple hundred Earth's atmospheres. But what you see is that when we go for the surface of the Earth, we can start with water at 0 degrees Celsius, and so it's at basically the freezing point, or what ice is. And as you raise the temperature, it basically follows this line, this dotted line, until you get to 100 degrees C, and then it starts to boil. But what this entire diagram shows is that depending on what the pressure is, you can actually have water at liquid states even if the temperature is much higher than 100 degrees. And so if you have much higher pressures, let's say up here, up at the top, water can remain liquid even at temperatures greater than 100 degrees, and water can also turn into a gas at much lower temperatures as long as the pressure is low as a result. Now, you can also create a similar diagram for hydrogen, and it ends up being a lot more complicated, but hydrogen does have a metallic liquid state over here, and then there's also what we think is a metallic solid state for hydrogen. And if you look at the pressures down here, we're not dealing with just ordinary pressures on the Earth, but this is 100 gigapascals, which is on the order of about 1 million atmospheric pressures on the surface of the Earth. So you really have to squeeze hydrogen by a huge amount to even begin getting it close to where it can become metallic. And people have actually, up until very recently, have not been able to actually create metallic solid hydrogen. This was more of a theoretical construct than something that we know that it actually exists. So, but physicists and chemists have wondered whether metallic hydrogen can exist, and they think it could. And actually, last year there was a paper that came out that touted the discovery or the creation of solid hydrogen. And what they did was they compressed hydrogen atoms in a pair of diamond anvils. So you have diamond up here at the top and then diamond at the bottom, and they squeeze the material. And normally, when the hydrogen is not compressed, you have two hydrogen atoms that are bound together to form a hydrogen molecule. And so that's what we see here at the left. But when you squeeze the hydrogen at sufficiently high enough pressure, it breaks apart the bonds that create the molecular hydrogen. And so instead you have free atomic hydrogen. And they believe that they were able to squeeze it enough to get it to form into a solid metallic state. And this is what they did. I was looking at the paper, and believe it or not, these pictures are not taken with like some really fancy equipment. The physicists actually just used their iPhone to take this inside their chamber. But what they argue is that when the hydrogen is still in its normal state, it's still transparent, and so what we're seeing is just light coming through the transparent hydrogen. And as you keep increasing the pressure, it then becomes solid black, meaning it doesn't really reflect any light, and it turns into a semiconductor instead of a conductor, which is what we expect metals to be. And finally, once they get it to the final state and they turn it into what they think is metallic hydrogen, it actually becomes shiny. So they were able to shine light and see light reflected from it. And so they didn't actually probe the actual properties of that metallic hydrogen, or what they think is metallic hydrogen. The only test that they did was to shine light and to detect whether it was shiny or not. And so there was actually still a little bit of controversy within the physics community about whether metallic solid hydrogen was actually created in this experiment or not. And so there are some people who are arguing for and some people are arguing against. And obviously, if the only thing that you're probing is whether it's shiny or not, there could obviously be some ways in which this material could get some shininess and make it seem like it's atomic metallic hydrogen, even though it's not. But assuming that it is, the authors of the paper that we're really interested in talking about today took some of their results along with results from other groups, including their own. Now, this was, as I said, this was the first group that ever made solid metallic hydrogen, or they claimed to have made it, but other groups have been able to create liquid metallic hydrogen. So they were able to use basically these new results as well as previous results. And what they did was they put them into a model for giant planets like Jupiter. And so the reason why we think metallic hydrogen is important is that because of the conditions, because of how massive these worlds are, not only Jupiter, but also partly Saturn. And then now we've been discovering many thousands of planets around other stars, and there are lots of planets that are Jupiter size or even larger. So it turns out that when you're dealing with these giant gas planets, even though we talk about hydrogen being the vast majority of the elements, of the matter in our universe, well, it turns out that if you lock up hydrogen in planets, in large planets, much of the hydrogen is actually not ordinary hydrogen gas, but it's actually metallic hydrogen. And so we think that a planet like Jupiter probably does have a dense, rocky, and icy core way at the center. It's still a debate about how much mass is located within that rocky, icy core. But outside of that dense core, you might have liquid as well as potentially some solid metallic hydrogen. And then only in the outermost, let's say perhaps 10% of the radius of the planet, do you actually have gaseous hydrogen. So basically, the inner 80 to 90% of Jupiter is actually filled with metallic hydrogen. And since Jupiter is the largest planet and it weighs, it's more massive than all the other planets combined, that means outside of our sun, most of the matter in our solar system is in the form of metallic hydrogen. And so what they did was to create models, and we know Jupiter to have a very strong magnetic field. That's what those bluish, purplish lines are. And it turns out that you can create a model of the dynamo that creates the magnetic field. And so they were able to use the latest observations about the properties of metallic hydrogen and to crunch their numbers about what type of magnetic field would be generated from Jupiter. And it actually matches the observations that we're getting back from the Juno spacecraft that's in orbit around Jupiter now. And then the other thing that they did was to also run the same model for different types of planets that we know to exist, that have been discovered, and then to also look at planets that are relatively close by. And what they find is that it is potentially possible from the magnetic fields that are generated by these planets for us to, if this model is correct, for us to actually be able to detect the radiation coming from these magnetic fields in the radio waves in the near future. Let's say not with the current technology, but perhaps with an upgraded, very large array, for instance. So, so this is a really good example of astronomy where we were taking, not only we're using observations from physics, from physics experiments, and throwing them into a theoretical model, but then also making predictions as to what you could potentially observe if this model was correct. And so people will undoubtedly continue to work on this model, either this team or their competitors, but eventually what we'll have to do is to actually make observations to see whether the planets that they're suggesting should have these strong magnetic fields actually have them in what they project.